Okay, so this video is going to include two examples of using source transformations to solve circuits, and then two examples of using delta Y conversions, again, to solve circuits, or to find equivalent resistance. So the first thing I want to start with is an example of source transformation. It's a simpler one than the longer one that I had. So let's say we have the following circuit. We have a 10 amp current source in parallel with a 10 ohm resistor, and then that is connected. I'm going to draw terminals here. We don't really need them in the circuit, but just to kind of understand that this is a current source that has then been connected to the following set of resistors. I just want to know what is the voltage drop across the 5 ohm resistor only. So importantly, the 5 ohm is not in parallel with the 10. The 5 and the 17 together are in parallel with the 10. So I could do that, combine, try and find the voltage across the terminals that way. Instead, what I'm going to do is come over here and say, well, look, if I could rewrite this in this format. So all I'm doing is I'm just replacing the current source in parallel with the resistor with its equivalent series connection. Then I just have one big series circuit going all the way around, and then it'd be perfect for voltage division. So let's do that. So again, what I'm doing is I'm kind of dividing the circuit this way, and I'm just going to use this part and make the equivalent voltage representations. So voltage source. Its polarity matches the polarity of the current. So if the current is increasing that direction, then the voltage is increasing. It's going to be in series with the 10 ohm resistor. That does not change. The voltage is going to be just V equals IR. So 10 times 10, or 100 volts. Dawns on me, you may not be able to see all of that. We'll go back over. So 100 volts. And then I'm just going to connect it up to what it was connected to before. So 17 ohms, 5 ohms. I'm trying to find this. Okay, now we just have one big series. We could look at this and do a KVL and just sum all the voltage drops. And then that would allow us to solve for current. And then we know the current through the 5 ohm, and then we can find it that way. Or this is voltage division. If I have these three resistors in series and I want to know the voltage only across this one, the voltage drops are all proportional to the relative size of the resistor. So the drop here is its proportion 5 out of the total resistors. So then I can say that the voltage drop across the 5 ohm resistor is just its part 5 over the total times the voltage source. So we're going to get 15.6 volts. So this is a case where this one was much easier to do, just a quick source transformation, easy to do, and then a quick voltage division. We're going to find that there are other ways to solve this, but in this case, this is really probably the easiest one. Okay, so now let's look at a little bit tougher one. All right, number 52. So let's just take a moment and look at this. Every time you look at a circuit, we're going to start asking what are two or three or four different ways to solve the circuit. And for now, we don't have a lot of ways that are systematic. We're going to get to that next week. But importantly, it's worth taking a look and trying to understand how the circuit is connected. And importantly, what I see here, in fact, let me draw in some nodes. I'm going to label these nodes. A, B, C, D. So if I look between these nodes, these two components are actually in parallel. The current divider is connected between D and C, and the resistor is connected between D and C. So we have parallel in this corner, parallel. In fact, all the corners are parallel. So what we're going to do, we're interested in the voltage across the 4 ohm resistor. Importantly, when I make this source transformation, the voltage across the terminals is what stays the same. The voltage across the resistor is not. Here, there's 0 voltage across the resistor because there's no current flowing. Here, there is voltage across the resistor. So what that means is because I'm interested in this voltage, I'm not going to transform this corner. So I'm going to transform all the other corners and then come back and look at the circuit. Okay, so let's get started. Let's do A to B. So I'm going to kind of draw it out this way. I'll draw it out maybe a couple of different ways for each corner. So here's A, and here's B. So all I've done here is just sort of, stretch it out. Make sure that you agree that it's still connected. The current source is connected, between A and B, and the resistor between A and B. It doesn't matter what configuration the wires take. Corners, circles, diagonals, it doesn't matter. Okay, so I'm going to take this. Resistor stays the same. Current source turns into a voltage source. Because the current is pointing down, that means the polarity of our voltage source is also going to be that direction, minus plus, going down. So minus plus, and the voltage is just equal to 2 times 2, 4 volts. Okay, so now we're going to do the same thing with B to C and C to D. Let's see if I can draw it another couple of different ways. Let's see. There's B and C like that. This one, the voltage source is pointing up. So I could draw it in that same diagonal fashion. With C and B in the same place. And I'm going to have a source and a resistor. The source will stay 2 ohms. The current is going from C to B. So that means my polarity of my source is in the same direction. It increases from C to B. And so that's going to be 2 times 5, 10 volts. All right, let's look at D and C to D. Let's draw this one this way. So again, make sure we agree that that's correct. So the 2.5 amp and the 4 ohm resistor are both connected between D and C. So that's correct. So now I can draw that this way. Here's D. Here is C. The resistor stays the same. The voltage source is now down in the same direction as the current. The current's going down, so that means we're increasing voltage going down. And so that's just going to be 4 times 2.5, 10 volts. Okay, so now we're ready to put all of that back together into one circuit. All right, so I'm going to start with drawing I'm going to start with drawing at the top. I'm just going to leave the top alone. So I'm going to essentially leave, in this case, A, B, C, and D, all those nodes in the same relative geometric organization. But instead, I'm going to draw like this. So here's A, and here's D. 2 amps going up, 4 ohms. Make sure you agree that those are connected properly. The 4 ohm resistor looks, it's not quite as directly connected. The line doesn't go straight from A to D, but it does go from D through this jog, through the 4 ohm, and to A. So this is connected in the same way. So now, let's just start going over from A. A now is going to have a resistor, and a voltage source to get down to B. The resistor is 2 ohms. And here again, if you'd like, go ahead and recheck. Here the current source is pointing down. So that means our voltage source is pointing down 4 volts. B to C, another resistor. I'm going to just come around the corner. Voltage source, 2 ohm resistor, 10 volt source. And again here, if we look at way up at the top, the current source is pointing from C to B, so that means I'm going to increase voltage from C to B. So that makes sense. And then lastly, from C to D, we have a 4 ohm resistor. And then again, we have the current that's pointing from D to C, so that means I'm going to gain voltage going from D to C. So minus, plus, 10 volts. Okay, so this is a much simpler circuit, because now most of it is in series. And it doesn't matter that we're kind of going back and forth between voltage sources and resistors. That doesn't matter. The total resistance in this path is just the sum of the resistors. And the total voltage gained through sources is just the sum of the voltages. So we just have to be careful how we add. Resistors just add, so 4 plus 2 plus 2, 8. The voltages, though, when I go from D, I'm going to climb up through 10 volts, so that's plus 10. Plus 10 more is 20. Come around the corner, but now I'm going to go down 4 volts. So 10 plus 10 minus 4, so 16 volts altogether. So 8 ohms for the resistance, 16 volts for the voltage. Okay, so again, we need to redraw. Every time that you have made a major simplification to a circuit, you need to just go ahead and redraw it. So let's see if we can do that. So this is number 52. So we're going to have this one. So we have 2 amps. We have 4 ohm resistor that we're interested in, 8 ohms, and 16 volts. That is a dramatically simpler circuit. So now we need to think about how we want the voltage here. And again, starting next week, we'll have some systematic ways to solve this, but for now we just have our list. We're not ready for current divider. We've got 1/2 that's parallel and 1/2 that's series. Importantly, we are looking for this voltage here. So we do not want to make too many changes to that. So I see parallel and I see series. My thought is convert this back to parallel on this side, and then the whole thing's in parallel. And then I think I can work with that pretty easily. So let's do that. So essentially what we're going to do is we're going to divide it this way. And I'm going to convert that right-hand side to a current source and a resistor. The resistor stays the same. The current goes in the direction of the voltage. The current is equal to V over R, 16 over 8, 2 amps. Oh, maybe you can't see what I just wrote. That's what I just wrote. Okay. So let's go ahead and finish connecting it. So now I'm going to reconnect that. So now we have 2 ohms. We have a whole lot in parallel. And remember that you can rearrange the order of parallel branches. It really doesn't change anything. So we have 2 amps going up here, a 4 ohm resistor of interest, 8 ohms, and 2 amps. Okay, so again, we can, just like in series, it doesn't matter the order of resistors and voltages. In parallel, it doesn't matter. I can combine the 4 and the 8 ohm resistor, and I can combine the currents. The currents are both going in the same direction, so they will add. am I interested in combining these? I'm interested in this voltage here. Do we agree it's the same as the voltage across the 8 ohm resistor? It is, because they are in parallel. They share the nodes, and so the voltage here is the voltage here. So I can combine those without losing that definition. So I'm going to combine these, and I'm going to combine these. So let's just keep writing in. We're interested in this one, and so it's going to be this one. So 4 amps here, because they're in the same direction, so they simply add. The resistor will be 4 in parallel with 8, which is 8/3. So now, to find the voltage of interest is just IR. 4 times 8/3, 32/3 volts. So this was a case where we went kind of back and forth. We simplified things, and then we found, even in our simplified circuit, that we would rather go back again, and that's not uncommon with source transformations. A lot of times you will do one to allow some simplification and then go back. And you may even go back and forth and back and forth. That is a viable way to solve circuits. Okay. All right, so let's look at another one. Here's another source transformation problem. And this is one where we're going to need to think carefully about the nodes to make sure that we understand what nodes are which. We need to identify what's in series and what's in parallel. So is anything in series? Yes, I see these two. And I don't think anything else. What's in parallel? Well, these two, those are pretty easy to see. The node here is the same as the nodes there, so these are in parallel. What about the 4 ohm and the 3 amp? Let me move it down at the point. Let's look at this side. Do they share a node? Yes, they do, because a wire counts as a node. Come on the other side. Do they share a node? Yeah, they do, because a wire counts as a node. This whole piece right here can be collapsed down to a single point. That wire does not matter. So it's clear to see, I think, that they share a node here, but they also share a node on the other side because there's nothing in the way. So these are also in parallel. So these are in parallel, and these are in parallel. So what I'm going to do then, and so those are in parallel, parallel, parallel. I sort of see some parallel here, but not quite. And so it kind of looks like the last problem, where we have parallel, parallel, something, and they're all kind of tied in series. So that suggests that if I change this to its voltage representation and this one, then that's going to clean up this side of the circuit. So let's start with that. So looking at this pair here, in fact, I'm just going to kind of draw it around the corner. So let's label this node A, down here B, label this one C, and that one D. So from A to B, I can do this. The resistance stays the same, the voltage is IR, so it's 8 volts. And then I can do the same thing between A and C. There's A, there's C, in this other corner. And we can see that the 4 ohm is connected to A, and the 3 amp source is connected to A. So I'm going to do the same thing. The resistor stays the same. The current is going from A to C. That tells us what direction our voltage source should go. And the voltage source will be 3 times 4, IR, so 12 volts. So that corner of the circuit cleaned up really nice. So now let's tackle, So I'm going to have A to C is series, A to B is series, B to D is series. So really it's just this corner, this CD corner. So let's take a look at that. If we look between C and D, we see that we have one resistor between C and D. And then remember, this is connected to C also. And then we have this series representation. So this branch and this branch are in parallel. But that's in series. So if I could change that to its parallel equivalent, then I'd have a whole bunch of things in parallel. So I'm going to change this to parallel and then do some combining. And then go back to series, because then I'll be in series going all the way around. All right, so how will I write this so it's clear? I'm going to take this piece right here. So let's rewrite that. So it connects C and D. So we have C. I'm going to change it into its parallel configuration. So between C and D, the 3 ohm stays the same. The voltage rises from D to C, so that tells us what direction we should have our current. The current is going to be V divided by R, so 30 divided by 3, 10 amps. Okay, so now let's take that. That's just the voltage, the source transformation. Now let's add to that. Right, we can add to that. So draw in the 6 ohm resistor, right? Because that's in parallel also. So now, again, we can see some simplification. 6 ohm is in parallel with 3 ohm, in parallel with the current source. So this, I can combine the resistors. 6 in parallel with 3 is 2. So this is actually equal to the 2 ohm resistor and 10 amps for my source. No, maybe you can see it again, sorry. 10 amps for my source. Okay, so this is what this corner is equal to. I am again going to like to put that into a series representation, so then I'll have series, 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 everything in series. So we need to change this. We'll go ahead and label C and D again. Change that into an equivalent voltage. C and D. The resistance stays the same. V equals IR in that direction. And it's in that direction because the current is going from, when we did it, from D to C. So that means the voltage is rising from D to C. So now we have all these series pieces that we can put together. So let's write our final circuit. And importantly, before we move on, here's I. We have not changed anything about the definition of I. That's important. Because if you change anything that includes the definition of what you're looking for, you're going to have to make sure to go back. You can't destroy the definition and then get the answer unless you go back again. All right, so let's put everything together. So we're going to have this one from A to C, so 4 ohms and 12 volts. And then from C to D, 2 ohms and 20 volts. From B to D just only has the 2 ohm resistor of interest. Really not left enough space. And then we have from A to B, we have the 4 ohm resistor and the 8-volt source. Okay, so now everything's in series, and I just want to know I. Oh, yes, thank you. So I just want to know I. So really, if I can just add up, I is just all the voltages around the loop divided by the resistances. But tell you what, that's one way to do it, but let's go ahead and use KVL just as some practice. So we're just going to do KVL around the loop. The I that we're looking for is going to be our mesh current. Okay, so we're going to just assume that our mesh current is going in the same direction. So KVL. We got to pick a place to start. So I vote for here. I usually start, I don't know why, in the bottom corner. So in the direction of the current, we have a 4I drop. We're going to gain 12 volts, so that's going to be negative. We're going to have another 4I drop, V times R times I times R, plus another 2I drop. 20 is a drop, a 2I drop, and then a gain of 8 volts. That was kind of long. So again, so we drop voltage here, we gain it here, so it's negative, drop, drop, another drop, drop, and a gain. So now we just solve for I. What do we get when we solve for I? We have 4 and 4 and 2 and 2, so that's 12I. Negative 12 minus 8 plus 20, 0. Okay, puzzling answer, but correct nonetheless. So don't let a strange answer necessarily throw you off. I mean, it's worth going back and double checking, but that's in fact the answer for this one. So again, this one was the idea that we had a same thing, parallel kind of connected in series. So if we can convert those to series, do some combination, you know, it helps us solve. And on this side, we had some series that if we could put in parallel, resulted in some simplification, and then back to series again. So you can kind of go back and forth. The other thing we could have done here is to add up all the sources. So we have negative 20 plus 8 plus 12. There's no source in this circuit. That's the other thing that we could do. 8 plus 12 minus 20. If there's no source for a resistive circuit, there's no current. All right, so that's that one. Okay, so now we are ready to do now we're ready to do some delta Ys. We'll do just a couple of these. They're just a little bit of a pain, I gotta tell you. But so let's look at why that might help us here. So how do you know whether it's going to help you or not? So let's look at this. In the future, we're going to learn how to do this using mesh current or node voltage. But for now, there's nothing in parallel, right? These are not in parallel. They share this node, but not that one. There's something in the way. And these are not in parallel. They share this node, but not this because something's in the way. So there's not a lot we can do there. But if we look at what happens when we do a delta Y conversion, I'm going to draw this in where you can see it. Now let's see if that helps us. Now the 6 ohm and this new resistor, those are now in parallel. They share this node and they share this node. This one, 6 ohm, and its are now in parallel also. This one's gone, and then this is in parallel with that. So now we've made it into a circuit where it's just a little bit easier to do some combinations. So we're trying to find the power here, so that means we know the voltage, we just need to know the current. So if we could actually make all of this into one big resistor, one equivalent resistor, then we know exactly what the current is coming from the source. So let's do some of that. So we are going from Y to delta, or if you want to think about it, T to pi. Okay, so that means, I'm just going to pull it out separately so we can draw a little bit more cleanly.